Record. Alright, welcome to Controls 2 CNTL3020 26 Winter, Fanshawe College, London, Ontario. This is week 9, March 11. And hey, we got Friday the 13th coming up, so it's the second time already this year. So I think some of us will be probably going to Port Dover this year twice. I'm not going there. All right. Let's start with this thing here. Where do I have my board? Here's my board. So, just right off the bat, let's see, based on what we have done so far, we're going to go something like this. Here is a rung, and here is the positive rail of the rung. Here's the negative rail of the rung, and we're going to insert a couple of instructions on this rung and see what is going to happen. Let's see if we can predict the outcome. So I'm gonna get a little eraser here. Gonna break this rung here, and we're going to break this rung right here. So of course on the left side we have the inputs, and on the right side we have the outputs. So on the input we're going to have an instruction that is marked as this symbol right here. Okay, and on the output we're going to have instruction as such. So now this instruction is tied to a switch. Let's say we're going to have a switch with a couple of terminals, and the switch looks like this. So it's a normally open switch. So this is tied to that thing right here, assigned. And of course over here, here's the output, and the output is going to energize whatever it is going to energize. So this is a ladder logic instruction right here. What is this instruction? Can anyone type or say what is this instruction called? What's the name of this instruction? What is the label of that instruction? This one right here. You can type or you can pipe in on what XIO. So this one here. Okay. So we got XIO. Examine if open. Yes. So this instruction is called examine if open. And what would be this here? All right. OTE. All right. So let's say this one here is this input, the examine if examine if open instruction is assigned to the data switch, let's say 01. All right. And that would be the data, let's say data input. All right. And this one would here be assigned to data output 05. Alright? So here's a switch number 1. Here's the contact terminal number 5. Let's just draw the contact number 5, and it's just labeled as 5. And in here we have connected, let's say, a simple light bulb that goes right to the ground here. Now we only could have on the output either logic 1 or logic 0, or logic true or logic false, or 24 volts or 0 volts. Alright? So we start running the program. The button is not pressed. It is as it is. We can just say here, this is going to 24 volts DC, and let's say that one is tied to ground, and this one here is assigned to that input right here. So examine if open. Is this switch open? Yes, it is open. So we're going to have a true here. The answer is true, which means the condition of this point right here is logic 1, which means it's going to have 24 volts at this point. That 24 volts is going to carry on to the output energized. Is this output going to be energized? The switch is open. You see here, the default condition of this instruction is that it is connected here, so it is closed. The instruction here, it is tied to the switch. The switch is not closed, it's open, so it's going to give us the answer to the question, examine if open, is going to be true, which means we're going to have a logic true here, even though the button is not pressed. Which means it is going to energize the output. We're going to have logic 1 or we're going to true, which is logic 1, which is 24 volts here, which means we're going to have 24 volts here on the output 5 because it's assigned to the output, which means yes, there is going to be light. And so as soon as we start making the program run, that light is going to be stuck on from the go. Now what is going to happen if we press the switch? So let's say, let me just choose a different color maybe. Let's get with red. We have red? Yes, we do have red. So let's say the switch is going to be pressed right here in red. Now, examine if open. Is the switch open? No. So the answer to the question is going to be false, which is going to give us logic 0, which is going to give us 0 volts on here. That is going to be carried over through the output, and we're going to have logic state of false or logic state of 0 or 0 volts on the output, and we're going to have 0 volts here, and we're going to have, well, no light. Alright. So in this case, we press the button to de-energize the output, which would be different if we had another case like this. Yeah. And we have something like instruction like this. So this would be examine if closed. This one also is output energize. That doesn't change. And now, if that is assigned to, let's say, well, if that is assigned to a also normally open switch, all right. Let's say this one is data input 03, right? And this could be assigned to data output. See, we had that one 5. Let's make it 07, right? So now, same. In both cases we have a switch that is normally open. Pressing that switch here is going to turn the light off, which is already on because of this instruction right here. And pressing the switch in this here, so switch true, light off. Over here, switch true, light on, depending on what the instruction is. I just have to get this thing, because sometimes we're going to say, okay, so is this true or false, or are here on the input? Well, we got to specify what is true, what is false. In this case here, true is the switch is actuated, which means 24 volts is applied. Based on 24 volts applied to this input, we're going to have the light off from the original state on. Applying 24 volts to the input in this case with this instruction, it is going to turn the light on. It's going to energize the output from it being, to change it from the state of being de-energized by default. Excuse me. Now, what I'm going to do here, I'm going to fire up something. Quickly going to go over a little bit here what we've done today, but I'm going to go quickly here. Just so you can have some reference that you can go back to. So I'm not going to go in detail as we did in classroom, but this way you're going to see those cool animations that I prepared for you. Did it for all night. All right, so here we have the inputs. Here we have the outputs. And over here we have the switches that are connected physically to those inputs. Flipping the switch on is going to provide 24 volts onto this. Flipping this switch is going to provide 24 volts onto this. It's just like connecting a wire from the positive terminal of the power supply to that. You can do it either way. You can either do it with the switch, if you want to quickly check it, check the logic, if you have done the program right. And then you can connect the rest of it. You can connect the limit switch, you can connect the sensor, you can connect whatever push button. And over here is the outputs. If the output is energized, it's going to have 24 volts appearing on that with a reference to the power supply, ground, or the negative rail, which is connected to ground anyways, quite often, if not all the time. And you're going to have the pilot light come on. And those are assignable. Alright, so quickly just concentrate on that part. Concentrate on a couple of those, just one row to make things easier. And magnify it. See how nice? At the rails, positive rail and a negative rail. And the positive rail has 24 volt DC. Negative rail has the 0 volt. Sits on the ground level. And then we can just start connecting things into a rung. So each connection, each of those connections looks like this right here, this rung. Here's an instruction that's going to be assigned, and here's an instruction going to be assigned. So this here rung looks quite horizontal visually, but this rung here doesn't look as horizontal visually, but it's still going to be represented. It's just going to have different number here and a different number here. And we consider the true state of true when there's 24 volts applied to the input, and if there is no 24 volts applied to the input, it's going to be pulled down to 0, which is going to be at the false state. Now here's a push button, and if we have that examine if closed, right? Examine if closed. So the switch is normally open, see if it's closed. Is it closed now? The answer is no. The answer is false. Then there's no 24 volt applied to this. The answer is false, so it's going to translate into the false on the output. So the rung is going to be false and the output is not going to be energized. Same thing with here and same thing with here. It's just they're assigned to different ports. Alright. Now you see here what happens? I go back and forth. We keep pushing this button here now, right? See that? Push this button. Excuse me. Examine if closed. Yes, the answer is true. So true here. Right? This one becomes true. This one, the answer to examine if closed becomes true. So that's going to give us a true 24 volts on this input here. That is going to translate because of this instruction. Examine if closed. Yes, it's true. So this side of the rung is going to be true. It's going to translate onto the true state on the output. Output is energized. This one here, examine if closed. No, it's false. We have false here. This false here. This open switch is going to translate into the false state on the input. That's going to give us 0 volts here. This is going to be translated into the 0 volts on the output. And the output is not going to be energized. And over here it is going to be energized, just like that one there. All right? Now, you see here, examine if closed. This is going to change to the examine if open. All right. So now we have instruction that's examine if open, if we have that over here. And just like we did in the beginning, we analyzed that. So examine if is it open. All right. Well, yes, it's open. So that is going to translate into the false here. See, this is where things are getting a little bit complex. This is going to give us a false state. The state is false, but the answer to the question is true. Is it open? Yes. But that translates into the state of false here, because 0 volts equals false. It's almost like we have to split our brain into thinking in 6th dimension or something. So this false here, because of the instruction examine open, this false is going to give us true here. Examine if open. Did we provide 24 volts into this here? No. Which means, is it open? Yes. This one here is, if it's open, I'm going to react. This one is asking, is this thing open? Is this one 0? If this one is 0, then I'm going to raise my hand. Over here, examine if closed. This one says, if this is 24 volts, I'm going to raise my hand. Okay? Go back here. Examine if open. All right. And over here, what do we have? Same thing. Is it open? Yes, it's open, which means there's a false here, which I'm going to energize because this input is not energized because of this instruction. Now we close the switch here. So you watch this switch right here. Closing it, okay, things are changing. See, watch this light right here. We push the switch, we turn the light off. Push the switch, turn the light off. This becomes false, this becomes de-energized. Examine if open. It's not open, which means there's 24 volts here applied, either by the switch turning on or running a lead, or running a lead through an external switch or a sensor or whatever else. It's going to give us 24 volts here. And if it's examine if open instruction, if this is in the state of true, then this is going to be de-energized. Right? And just a summary of the instructions. Examine if closed, symbol. Examine if open, symbol. Output energize, symbol. Output latch. Output unlatch. So the difference between that is that if it's just an output energize, pressing that button or changing the state into the true question of whatever the instruction is asking, it's going to trigger the change of the output. But as soon as we go back, we release this switch, the spring-loaded switch springs back, it's going to go to the previous state. And but if we have this instruction here, output latch, we trigger the input, output is going to change, and if we untrigger the input, the output is going to stay as it was when triggered, until it's being told to do otherwise, which would be output unlatch. So you could have two buttons assigned to trigger the same output. You can have a button that is going to tell the output to turn on and stay, and another button that you press that's going to tell the output to turn off and stay that way. So latch and unlatch. We have already gone through that today, so later on we're going to concentrate on making a latch out of the logic on the Studio 5000, and we're going to experience how different that is from the logic in real life. I'm not going to spend too much time on this because we already did that in class, and we are going to revisit that thing anyways. All right, so now a couple of exercises here because I'm going to launch a quiz on you soon. So let's do something like this. We're going to concentrate on one thing, and we're going to grind it a little bit and see if it actually sinks into us. All right, so we're going to have the De Morgan's theorem. We're going to solve some problems here. De Morgan's theorem, as a reminder, if we have a negation bar on the output of an AND gate, we could substitute that with negating the inputs separately on an OR gate. Just like so. Here's an AND gate, and here is the inversion bubble. So you could have an inverter connected to it, or you could have the inversion bubble, which would make this thing a NAND gate, right? So here's A and B, and on the output, it's that here. This is this point right here. And that's equal to the same thing as if you had an OR gate and you had the inversion bubble separately on the inputs right here, and that's going to give you the output. And if you apply 0, 1, 1, 0, 1, 1, or 0, 0, you're going to get the same results on the truth table here. And of course, if you want to break the bar, the negation bar on the OR gate, you can break that bar, but you have to substitute that OR with an AND, and over here you substitute AND with the OR. Okay? And this one, the second one here, looks like this right here. So you thought that was interesting. If you think that's interesting, well, try this. I'll let you look at that later when I post it. Okay. All right, let's see the first problem here. Here we have a problem to solve. Let's simplify this thing to the simplest term. Just get my phone here so I know how we're doing with time. Okay, cool. All right. What do we have here first? Well, what can we do first? See that here? That looks something like this. Here's the OR, here's some expression, here's another expression. There's a negation bar right here. So here's one expression here, and here's another expression here. We can break that bar by breaking it and substituting this OR with an AND. So let's do that. See here? From that we got that. We broke that bar, and we changed that into the AND instead of OR right here. See? So now we have this expression right here, and we have this expression right here with this bar broken. Well, what else can we do with this now? Can we simplify that? Well, yeah. You see, we have not, and not here, or not here, but not yet. Right? We could just simplify that, because negative of a negative is, well, they cancel. So from that, we can just eliminate that, because one negation eliminates the other one. So it turns into this, and that negation bar, the not bar, stays, because there. There's something else we could do with this. Well, yeah, not exactly De Morgan's theorem, but we could distribute those. See that? A or B and A and not B. What can we do here? Well, we could distribute this. A and A over here, and not B. See, A and not B. A and not B. So we have that connected, that A with these two, and we just group them together. Or we could do the same thing with the B right here. B and A, B and not B. So B and A and not B right here. That comes when it comes to the distributive properties. We're going to concentrate on that another time. Now, since we have those things here, if we have A and A, that is going to give us A. So these two here we can just substitute with just one A. A. And if we have B and not B, so you can just imagine that you have a gate right here. This will be AND gate. So you have an AND gate with couple of inputs and one output. So this is the output right here. Now this is an AND gate. So if we have B, we're going to have, let's say, 1. And if it's not B here, then we're going to have automatically, this is going to be 0. 1 and 0 is going to always give us 0. See the truth table of an AND gate? 0, 1, 1, 0, 1, 1. These are the inputs, and here will be the outputs. Both of the inputs have to be on for the logic on the output to be 1. Otherwise, we get zeros here. So they will never be the same. The other way we can draw this is if you have an AND gate. Here's the output. Here's one input, and here's an inverter, like a triangle with the inversion bubble, and that is connected here, and these are connected together, and this would be B here. So whichever, if you put 0 here, it's going to translate into 0 here, and it's going to translate into 1 here. If you put 1 here, it's going to translate into 1, it's going to translate into 0 here, and it's going to translate into 1 here. They're not be the same. It's always going to be 0, so that's why B and not B is going to give us 0. So over here we have that B and not B. So we could, from that expression, we got A and A that goes into A. So these two here become that, and not B, so that one just stays. But here is a B and not B, so that's going to be give us 0. So it's going to be A and 0. Whatever and 0 is always going to give us 0, so that is going to be 0. But that's going to be an OR gate right now. So look at this. Over here, this expression right here, we have an OR gate. And we have, no, sorry, what am I doing? We have, okay, we're looking at this expression right here. Since A and 0, so that's going to be 0. So over here we have that, this expression here, that A and not B. Alright, we have going into this place here, and over here we have 0. And that's an OR gate, so 0, 0, 0, 1, 1, 0, 1, 1. At OR gate, truth table is, that's not going to give us, is one of them open, active? Yes, so it's OR. Either this or that is going to give us 1, 1, 1. So if we have a 0 here, and if this whole thing becomes 1, then we're going to have 1 on the output. If this whole thing becomes 0, then we're going to have 0. So the output is going to follow the input here. So we could just eliminate that. And here's the final expression. That's the simplest. That's the simplest. Here's the final answer. All right. On that. Okay, let's take a look at this now, second one. How much time do we have left? 41. Let's do one more, and I'll let you do the third one by yourself. See if you can get that. All right. Again, we are practicing De Morgan's theorem. Right? All right, so we have this expression right now here. Whatever the output F, we call it F in this case. And we have that. Is there any negation bar we can we hit this thing from any angle? Yes, we can try to break this bar. So now we have that expression right here and this expression right here. Here we have an expression, and here we have an expression, and in between them there is that and. So we could break this bar and change that into OR, which is exactly what we did here. You see that bar is broken, and that and is turned into OR right now. So we have that. Okay. What else can we break? Now we can break this bar. So we have this expression, and we have this expression, and we can break this bar and change that into AND. Okay? Which is, that's the explanation of that right here. So that expression right here, see this here? This one right here is this one right here. Right. Except especially this one right here. Alright, so then we fill out the rest of the equation, because we still have to not forget about that. So now we got this. Have that bar broken. And because over here we have those two bars, it's going to look like this. Right here. And double negation is just eliminates itself. So there you go. A and B and C or not D. Here's the final answer. Right? That's a simple. That's can't simplify it anymore. What would it look like? Let's see if you can draw it. There's a big OR gate. That's the right here. That's the F. All right. Now we have as inverter, and this is going to be D. And over here we have A, not A, B, and C, so we could have a 3-input AND gate there like that too. So this could be C, this could be B, and we will have an inverter going on here, and this would be A. So this is how the circuit would look like. Simple as that's can't get it any simpler than that in this case. All right. If you have a pen and paper, I'm sure you do somewhere. See if you can break this one. I'll give you a couple. I'm going to be waiting for some suggestions. What would be the first thing that we want to concentrate and hit on? I got a windy night. What would you hit first in this expression? Anybody awake? I'm gonna sip of coffee. With a foamy milk. Hard to type with top lines. With the top lines. Okay. So, break the largest line first. Good. All right. So we're going to break this line. Awesome. Come on. There we go. So we get this. Now, when we have things looking like that, how can we clean this up? Then break every line. Well, we don't, like over here, we don't have to break every line. Look at this. Look what we have. We have double negative. So we could just eliminate these two. This one can be eliminated. And this one can be, because they are of the same length. They cover the same thing. So look. Here. All right. Anything we can do with this? Here's the answer. There's two answers here. ABC or ABD. Look at this. Or you can have something like that. Yeah. $49. We should start wrapping things up. Okay, so there's going to be a couple more examples here. When I post it later on tonight, you can just tackle those, because I want you to be comfortable enough to do this thing on the test when you get the pen and paper doing this. So that's why I try to concentrate on one thing. Right? Well, why don't we just do it quickly here? Block the longest line first. Look, we have that and we have that. Oh, that can be eliminated. And we get this here. And that's pretty much the final answer. You can just drop the brackets or the parentheses. So this one solved in 3 lines. Is there another one? Okay. So here's the De Morgan theorem. Can you break this line when you have 3 expressions like that? Yes, you can. You can do it with two terms, or you could do it 3. Oh, look. Boom, just like that. That you can do also. Now, here this not X becomes X. This is not Z becomes Z. Here's the final answer. 2 lines. See? Over here, I think that's the last one. Break this line. Kaboom. This one gets eliminated. Then you can De Morgan that. Huh? See here? This it gets eliminated. stays just like that. This OR carries on. This can be demorganized, and that's it. There's no more terms that we can do. That's the last slide. Longest bar. Hit this one first. Change this OR into AND, and there's a bar. It's kind of hard to see. And there's the double. Eliminate that. That becomes AB, because not, it means yes. Alright, see that here? Okay. Well, is that the final answer? There you go. Can't get any simpler. Let's see this thing crash. Okay, ready? Alright. Okay, that's it for today, and I will see you next. I'll see you this week during the lab. Cool. Thank you so much for being here and for paying attention, and thank you for being here for yourselves. And I will see you when I see you.